Okay, this video is for both December 14th and 15th lesson, so I can take most amount of questions on Tuesday on 15th. Okay, first, let's look at this differential equation, which is known as a periodic one. So this has to do with the seasonal growth. You see the cosine function here, so with the r, so that is designed to synchronize so that it goes through the 4 seasons of the year. Okay. And then, once again, we start with the initial population P naught. First, let's separate the variable. So we have dP over P, and leave everything on the other side. K cosine RT and dt. Now we integrate, and this is ln, and we are sure. And the other side, we have K and sine RT, therefore chain rule over R here. Okay, that's ugly. So K over R, like that, and plus C. Okay, then write it into exponential form. So we don't need a plus or minus because population is positive. So e to the K over R sine RT plus C. But we'd rather want to write it as P is equal to some other constant A, e to the K over R and sine RT. Okay, where my A is equal to e to the C this time. Good. Now we apply initial value conditions. So at 0 and P naught, we are substituting P naught to P, so it becomes P naught. And the other side, t, once you substitute 0, sine t is equal to 0, therefore e to the 0 is 1. So a is equal to p naught. Substitute it back, so we have p as a function of t is equal to p naught and e to the k over r, some constant, times sine rt. Now the question is, what does this function look like? Is it exponential growth function? Is it decay? Or is it some kind of periodic function? Okay, I have graphed this thing out. So let's see. Surprisingly, it is periodic function. Now, if you think about it, that makes sense. So this right there is P naught. And we go to the season because many species only have offsprings at certain time of the year. Okay, so the population goes up and comes back down and goes up and comes back down. See, when sine is positive, this looks like exponential growth function, but then inevitably sine will be turned into negative, then you go through exponential decay and then growth and decay. So that's why this part is wider than the peak up there. Okay, now second example, this is for Tuesday, December 15th. This is not really about this chapter, although there is a similar problem like this, but this is mainly for your physics class. This is what's known as a second order differential equation. So the force of the spring, when you compress the spring or stretch the spring, let's say this is an equilibrium right there. This is when x is equal to 0. And if you stretch it about that much, whatever that distance is, so this is what we call x, okay? And then spring fights back if you try to stretch it and pulls it back to you. So therefore, there's a negative sign. So the direction of the force of the spring is opposite direction of the motion. So if you stretch it, spring wants to pull it backward. If you compress it, then spring will push it back. So this is negative and some constant of proportionality. This is known as a spring constant, n times the amount of displacement. Okay, and also F is equal to ma, Newton's good old second law. So if you equate the two, then what we have is ma is equal to negative kx. But then acceleration is a second derivative of position. So what we have is m, and then second derivative of x is equal to negative kx, dividing both sides by m. So we have second derivative of x is equal to negative k over m x. Okay, now this cannot be done with the separation of variable, but guess and check is a really good way of solving differential equations in many instances. So let's think logically. Suppose we pull this thing, so stretch the spring that much, and then we release it, and suppose that is the whatever the original displacement. Okay, we can call that x naught. Okay, and we release it, then spring will oscillate back and forth, assuming there's no friction. If there's a friction, then it'll actually die down and reach back to the equilibrium, but that is second year college stuff. So assuming there's no friction, then it'll indefinitely oscillate. And then last year you learned that this is sinusoidal function. So why don't we take a guess? We'll say guess with x, which is function of t, is equal to some kind of a and then cosine t. But then once you write cosine t, there's no guarantee that the period of this will be 2 pi, because this thing has a period of 2 pi. So we don't know. We have another unknown. So a is an unknown here, and then we'll put omega, some kind of which angular velocity that you learned it in angular velocity packet. It turns out to be the same number, but you can say a and a b. Okay, now we'll take a derivative. So we'll check if this is a solution to our differential equation. So if we take a derivative, then what we have is negative a and then sine omega t and then chain rule. So we have omega here. Okay, take another derivative. So we have a second derivative is equal to negative a and pick up another chain rule, omega square and cosine omega t. Now we want to know if this thing will satisfy this differential equation with this initial condition, 0 and x naught. Okay, let's see. So we substitute this expression to the left-hand side of the differential equation. So we'll have negative a omega square and then cosine omega t. And the right-hand side, we substitute this expression over here. So we have negative k over m from the differential equation and our x, which is a cosine omega t. Well, look, we have a fighting chance. A cancels out. Cosine is the same thing. So as long as this is a solution, as long as my omega square happens to be k over m, that tells you your omega is, oh, that's ugly. Omega is equal to square root of k over m. And this is precisely what your physics book tells you. So x for now, function of t, is equal to some unknown, still unknown constant a, and then cosine and square root of k over m t. Now, how do we figure out a? Well, we apply initial condition, which is 0 and x naught, and substitute it here. So this side becomes x naught. And once you plug in 0 to t, cosine 0 is equal to 1. So that's our a value. So finally, that gives us our x. Function of t is equal to some kind of initial displacement, x naught, and cosine and square root of k over m t. How about that? This is not really the scope of this chapter in our book, but this is a differential equation nevertheless, and one problem like this shows up in your book, so here we go. Okay.